Welcome to chemistry classes. In this video, we are going to discuss about group 18 elements. Group 18 elements. This is the last part of P block elements. Here, group 18 elements. Group 18 elements also called noble gases. Group 18 elements also called noble gases. Noble gases or inert gases. Noble gases or inert gases. These elements are highly unreactive. Noble gases are helium, neon, argon, krypton, xenon. These are noble gases or group 18 elements. These elements are highly unreactive. Okay, that's why these elements also called inert gases. Inert gases. Okay, all these elements are in gaseous state. All these elements are gaseous state and they are highly unreactive. Okay, they are highly unreactive. That's why these elements forms few compounds. Noble gases form few compounds only because these elements are highly unreactive. Okay, next one we have to discuss here electronic configuration of noble gases. Electronic configuration of noble gases NS2 and P6. You can see here electronic configuration of noble gases NS2 and P6. They have complete electronic configuration in S subshell, also P subshell. Except helium. We know helium atomic number 2, so it is 1s2. Except helium, all other noble gases, their general electronic configuration NS2 and P6. Okay, so there is one exception case, helium. Next one, ionization energy. Here, generally noble gases, they have higher ionization energy because here they have stable electronic configuration. Group 18 elements, they have stable electronic configuration. They are stable, highly stable. So we have to give more energy to remove outer shell electron. That's why group 18 elements showing higher ionization energy in P block. Okay. Similarly, ionization energy decreases from top to down. In group 18, ionization energy decreases from top to down because size of the elements increases, atomic size increases. Okay, so distance between nucleus and the outer shell electron increases and we have to give less energy to remove outer shell electron. So here generally we have to understand here group 18 elements showing higher ionization energy. Ionization energy in group 18 decreases from top to down. Clear? Next one we have to understand here electron gain enthalpy. Electron gain enthalpy. We discuss here they have stable electronic configuration. Group 18 elements, they have stable electronic configuration. So they have less tendency to accept electron. Less tendency to accept electron. So group 18 elements showing less electron gain enthalpy. Less electron gain enthalpy. Or we can say group 18 element showing higher positive electron gain enthalpy. Higher positive value for electron gain enthalpy. Higher positive value for electron gain enthalpy mean we have to give more energy to add one more electron to group 18 elements. Okay, so here this group 18 elements, they have less tendency to gain electron. Okay, they showing higher positive value in electron gain enthalpy. Clear? Okay, next one we have to discuss here different properties of noble gases. Noble gases are colorless, tasteless, odorless gas. Okay, noble gases are colorless, odorless and tasteless and they will exist in the form of gaseous state. We discussed already. Okay, and here noble gases are sparingly soluble substance. They are sparingly soluble substance. Sparingly soluble substance substance mean they are partially soluble in water, sparingly soluble in water or partially soluble in water. Clear? And here melting and boiling point. Melting point and boiling point of noble gases are very less. Melting and boiling point of noble gases are very less because interatomic force of attraction are very less. Interatomic force of attraction mean force of attraction between two adjacent atoms. Here noble gases are monoatomic. Monoatomic means they will exist in the form of single atom. Noble gases are monoatomic. Okay, noble gases are single, they will exist in single atomic form. It means they are monoatomic. Okay, they are monoatomic. In case of hydrogen, oxygen, nitrogen, we know they are diatomic. Diatomic means they will exist in the form of two atoms joined together. That is diatomic. But here noble gases are monoatomic. They will exist in the form of single atom. That is monoatomic. And here we discussing here melting and boiling point of noble gases are very less because interatomic force means force of attraction between two adjacent atoms. Okay, it is called dispersion force. Interatomic force of attraction or dispersion force. It is very weak force of attraction. So less energy needed to break this bond. That's why noble gases showing very less melting and boiling point. Okay, and helium showing lowest boiling point 4.22 Kelvin. Okay, here helium showing lowest boiling point out of all known substance. Out of all substance, helium showing the lowest boiling point. This boiling point is 4.22 Kelvin. Clear? Okay, next one we have to discuss here chemical reactions of noble gases. Chemical reactions of group 18 elements. Generally we can say noble gases are highly unreactive. Here group 18 or noble gases, they are highly unreactive. These are the reason for their unreactivity. They have stable electronic configuration. They have complete outer shell electronic configuration. Okay, except helium, all other gases showing this electronic configuration NS2 and P6. They have stable electronic configuration. Okay, also these elements, they have very high ionization energy. They are stable. So they have very high ionization energy and their electron gain enthalpy showing very high positive value. So these are the reason. These are their reason to show their high unreactivity. So here noble gases or group 18 elements are highly unreactive. These are the reason. Here first reason, they have complete electronic configuration. They have complete outer shell electronic configuration, or we can say they have stable electronic configuration except helium, all other elements showing NS2 and P6. The ionization energy value is very high. Electron gain enthalpy, these elements, they have very less tendency to accept electron. Okay, and they showing very high positive electron gain enthalpy. Okay, we discuss noble gases are highly unreactive. They make or they produce very rare compound. They produce rare product. Okay, so look here, the scientist Neil Bartlett, he made a compound. He made a red compound O2 PTF6. This is one red compound made by this scientist Neil Bartlett. Okay, and in this compound he studied clearly and he observed that the ionization energy of molecular oxygen, the first ionization energy of O2 is 1175. In this compound, first ionization energy of oxygen is 1175. And he observed that it is very close to first ionization energy of xenon. Okay, here this scientist made a red compound. This is the red compound, and here he observed the first ionization energy of oxygen is 1175 kilojoule per mole, and he observed that it is very close to first ionization energy of xenon, 1170 kilojoule per mole. Okay, and this study helps to produce a new type of compound, new compound of xenon, similar like this here O2 plus PTF6. Similarly here xenon PTF6 instead of oxygen here xenon. Okay, this is the first compound of noble gases made by Neil Bartlett. Okay, and here he made this compound by mixing hexafluoroplatinum with xenon. Hexafluoroplatinum mixed with xenon, and he made this type of compound. Okay, later study there are many different type of noble gases compounds of noble gases discovered later. Okay, next one we have to study here different compounds of xenon. Xenon and fluorine form different type of compounds. Xenon and fluorine form three different type of binary compounds. Xenon and fluorine form three different type of binary compounds: XeF2, XeF4, XeF6. These are the three different type of binary compounds formed by reaction between xenon and fluorine. Okay, and see here xenon and fluorine simply reacting at a different temperature, it forms xenon fluoride. Xe and F2 form XeF2. Xe and 2F2 form XeF4. Xe and 3F2 form XeF6. Okay, they form at different temperature and different pressure. Look here, first one xenon and fluorine form XeF2 at 673 Kelvin and 1 bar pressure. And here Xe reacted with fluorine form XeF4 873 Kelvin and here 7 bar, here pressure 7 bar. Xenon reacted with 3F2 form XeF6, here 60 to 70 bar, here high pressure 60 to 7 bar pressure and 573 Kelvin. So these are the three different methods to prepare XeF2, XeF4 and XeF6. There is one more method to produce XeF6. XeF4 reacted with O2F2. It produced XeF6 and oxygen. XeF4 reacted with O2F2. Produced XeF6 and oxygen. So here we learned three different methods to produce XeF2, XeF4, XeF6. So these are the three binary compounds or three binary products formed between xenon and fluorine. Okay, so here we learned different type of binary compounds of xenon fluoride: XeF2, XeF4, XeF6. These are colorless solids. These are colorless crystalline solid, and they will sublimize at 298 Kelvin. These are colorless crystalline solid. They will change to gaseous state at 25 degrees Celsius or 298 Kelvin. Okay, and here they are strong fluorinating agent. They are strong fluorinating agent. They help to add fluorinating agent. Similarly, they will hydrolyze easily. After hydrolysis, they release xenon. Look here, XeF2 after dissolving in water, it forms xenon gas. It releases xenon and it will form aqueous hydrogen fluoride. Also it release oxygen gas. So here xenon fluorides are highly soluble in water. After dissolving this, it will release oxygen and xenon. Okay, and aqueous hydrogen fluoride formed. And here we learned XeF2, XeF4, XeF6. XeF2, it is linear structure. XeF2, it is linear structure. XeF4, square planar. XeF4, square planar. XeF6 mean there is 6 bond pair electron and 1 lone pair electron. XeF6 mean you can see here structure, there is 6 bond pair electron and 1 lone pair electron, and it's showing distorted octahedral. XeF2 linear, XeF4 square planar, XeF6 distorted octahedral. Okay, so here we discuss xenon fluorides are colorless crystalline solid. It will sublime at 298 Kelvin and they are strong fluorinating agent. It will hydrolyze very easily and release oxygen gas, xenon gas, and also we discuss their structure. Okay, we discuss different type of binary compounds of xenon fluoride. This xenon fluoride reacted with fluoride ion acceptor. Here we have one xenon fluoride. Here PTF5. It is fluoride ion acceptor. It will accept one fluoride ion. After reacting, xenon fluoride reacted with the fluoride ion acceptor, xenon fluoride will change to cationic species. Xenon fluoride will change to positively charged species. Clear? So here we discussed xenon fluoride reacted with fluoride ion acceptor. It will accept one fluoride. Then this species will change to positively charged particle. Okay, cationic species. Similarly, xenon fluoride reacted with fluoride ion donor. Okay, here we discuss fluoride ion acceptor. Next one we have to discuss here xenon fluoride reacting with fluoride ion donor. It will donate one fluoride ion. After that, xenon fluoride, it will change negatively charged species. Okay, anionic species will be formed. Clear? So here we discuss xenon fluoride reacted with fluoride ion acceptor. Then xenon fluoride will change to cationic species. Xenon fluoride reacted with metal fluoride. Metal fluoride mean here fluoride ion donor. Metal fluoride mean here metals such as sodium, potassium, rubidium, cesium. This type of metal fluoride, they will donate fluoride ion. After that, xenon fluoride will change to anionic species. Cationic species and anionic species. Okay, cationic species here reacting with fluoride ion acceptor. Anionic species. Anionic species mean fluoride ion. Xenon fluoride reacting with fluoride ion donor. Here this is fluoride ion donor. Clear? Okay, we discuss xenon fluoride compound. Next one we have to discuss here xenon oxygen compound. Xenon fluoride, after hydrolysis it forms xenon oxide compound. Already we discussed xenon fluoride. Next one we have to discuss here xenon oxygen compound. Here xenon oxygen compound, specially we have to study here XeO3. XeO3, xenon oxide compound. Okay, here xenon fluoride, after hydrolysis it forms XeO3. It forms xenon oxygen compound. Clear? Look here, XeF4 and XeF6. Xenon fluoride, after hydrolysis it forms xenon oxide compound. Especially here XeF4 and XeF6, after hydrolysis it forms xenon oxygen compound. See here, xenon fluoride XeF4, after hydrolysis it forms xenon oxide XeO3, hydrogen fluoride and oxygen. Also we learned before xenon fluoride compound, after hydrolysis it forms xenon. So here xenon fluoride, after hydrolysis it forms xenon oxide. Okay, especially here XeF4. XeF4, after hydrolysis it forms XeO3. Remember here XeF4, after hydrolysis it forms xenon oxide XeO3, hydrogen fluoride, xenon and oxygen. These are the different compounds formed XeF4 after hydrolysis. Similarly XeF6. XeF6, after hydrolysis it forms XeO3 and hydrogen fluoride. Okay, XeF6, after hydrolysis it forms XeO3 and hydrogen fluoride. Okay, next one we have to discuss here partial hydrolysis of XeF6. Here complete hydrolysis of XeF4 and XeF6, it produces XeO3, xenon oxygen compound. Partial hydrolysis of XeF6, it do not produce XeO3, it produces different type of compound called XeO4 and XeO2F2. Xenon oxyfluoride. This is called xenon oxyfluoride. Partial hydrolysis of XeF4, it produces xenon oxyfluoride. Xenon oxyfluoride means XeOF4, XeO2F2. These are two xenon oxyfluoride. So complete hydrolysis of xenon fluoride produce xenon oxide XeO3. Partial hydrolysis of XeF6, it produces xenon oxyfluoride. There are two different type of xenon oxyfluoride, XeOF4, XeOF4. Second one XeO2F2. These are the two different type of xenon oxyfluoride. Look here, partial hydrolysis of XeF6, it producing XeOF4, XeOF4 and hydrogen fluoride. Also look here, XeF6, another chemical reaction, similar way, two possibility. There are two possibility for partial hydrolysis of XeF6. One is XeOF4 formed. Another partial hydrolysis, it produce XeO2F2. We discuss here XeOF4, XeO2F2. This type of different compounds are formed on partial hydrolysis of XeF6. Clear? Next one we have to discuss here XeO3. XeO3, it is colorless explosive solid and it has pyramidal structure. Okay, XeO3, it is colorless explosive material and it has pyramidal structure. Clear? Similarly here XeOF4, xenon oxyfluoride. XeOF4, it is colorless volatile liquid. It is colorless volatile liquid, and here XeO3, it is colorless explosive material. And we discuss here XeO3, it is pyramidal structure. Similarly here XeOF4, it is square pyramidal structure. XeOF4 square pyramidal structure. XeO3 pyramidal structure. Okay, pyramidal and square pyramidal. Pyramidal which one? XeO3. Square pyramidal which one? XeOF4. Clear? So here we discuss xenon oxygen fluoride, xenon oxygen compound. Xenon oxygen compound means XeO3. This xenon oxygen compound formed by hydrolysis of XeF2 and XeF6. Okay, on hydrolysis this compound xenon XeF4 and XeF6 on hydrolysis it produce XeO3, xenon oxygen compound. Partial hydrolysis of XeF6 it produce xenon oxyfluoride. Xenon oxyfluoride means XeOF4, XeO2F2. These are xenon oxyfluoride. Okay, after that we discuss here XeO3, it is colorless explosive solid. Okay, colorless explosive solid. XeO3, it is pyramidal structure. After that we discuss here XeOF4. XeOF4, it is colorless volatile liquid. Colorless volatile liquid and it has square pyramidal structure. Clear? Okay, next one we have to discuss here different uses of noble gases. Different uses of noble gases. First one, helium. Helium has very low density and unreactive. That's why helium used in weather balloon. Helium used to fill in balloon because helium has very low density and it is unreactive. Okay. Also, helium used in cryogenic engine to conduct chemical reaction at very low temperature. Helium used in cryogenic engine to conduct chemical reaction at very low temperature. Next one here, helium used to make powerful magnet. Helium used to make powerful superconducting magnet. Powerful superconducting magnet, such type of magnet used in nuclear magnetic resonance spectroscopy. Okay, also used in spectrometer, NMR, nuclear magnetic resonance, and another one magnetic resonance imaging. Magnetic resonance imaging. Okay, MRI. Okay, so here helium used to make powerful superconducting magnet. This type of magnet used in NMR, spectrometer, MRI, etc. Okay, also here helium also filling with oxygen in modern diving apparatus. In modern diving apparatus, helium mixing with oxygen. Because helium is very less soluble in blood. The solubility of helium in blood is very less. That's why helium mixing with oxygen in modern diving apparatus. Okay, so these are the different uses of helium. Helium is very less reactive and it has very low density. That's why helium used to fill in balloon. Here helium used in cryogenic engine to carry out various chemical reaction at very low temperature. Okay, also helium used to make powerful superconducting magnet. Such type of magnet used in NMR, MRI, spectrometer, etc. Okay, and here in modern diving apparatus, helium mixing with oxygen, because helium has very less solubility in blood. Okay, next one we have to discuss here different uses of helium, different uses of neon. Sorry, helium finished. Next one we have to discuss different uses of neon. Neon used to make different type of discharge tube, fluorescent lamp, etc. Also neon used to make neon bulb. This type of neon bulb used in botanical garden, also used in greenhouse. Okay, next one we have to discuss here argon. Argon used to make inert atmosphere, especially in metallurgical process. In the extraction of metals, we have to use very high temperature. So here such a situation, argon used to make inert atmosphere. Also argon used to make electrical bulb. Okay. Okay, so these are the things we have to discuss in this video. Okay, so thank you for watching this channel.